Hi y'all, in this video today we will be taking a look at how to evaluate a limit using some of the limit laws. And in your resources for your class you probably have all the limit laws written down somewhere that you can reference, but we'll just be going over how to apply them or use them within this video. So in the first question we're just finding the limits here. The limit as x approaches 4 of the cube root of x plus 23. The first thing that you should remember about a limit is that if you can directly substitute in that value, then try it. So for example, can I evaluate the cube root of 4 plus 23? 4 plus 23 is 27. So can I evaluate the cube root of 27? Yes, in fact, I can. It's 3. And let's just verify why, in fact, this is the limit. Okay, so if I type in the function y equals the cube root of x plus 23, and if I go to window and maybe just shrink my window down a little bit. So for x values, for example, I just went from -2 to 6 because again, I'm really only concerned with this x value of 4 to the left and to the right and add that value. And the y min being -2 just allows me to see the axes and a y max of 10. So let's just see if this gives us a good picture here. All right, so here's my graph. It does appear to be continuous, but again, these looks can be deceiving, so certainly we'll use our calculator to help us. As x approaches 4, that's both from the left and from the right, so I have to look 1, 2, 3, 4, so it'd be about right here. So does the left limit appear to be the same as the right limit? It appears so, but we can certainly test it. You can do that one of two ways. You can go to your table setup if it's not set up already for ask for the independent variable. I would do that now. And then when you go back to the table, if you are approaching 4 from the left, your x value is something like 3.99 or 3.999. That gives me a y value or output close to 3. And as x approaches 4 from the right, I would be a little bit greater than 4 or 4.001, for example. And that gives me a y value of also approximately 3. And if x is equal to 4, that is also 3. So yes, the limit should be 3. You can also look back at your graph and use your calculate menu, which I like. So second trace or calculate. Calculate a value when x is 4. And this is an actual point on my curve, 4, 3. All right, so looking at number 2 now, a limit as x approaches 5 pi over 6 of sine of x. So here is my curve that we are looking at, and we should know something about the curve of sine of x. And also, I should know that I can directly substitute in 5 pi over 6. There's no restrictions, so let's evaluate what is sine of 5 pi over 6. So most of us would immediately go to our unit circle idea here, where I have 0 on the positive x-axis and pi on the negative x-axis, one complete rotation being 2 pi. 5 pi over 6 is 1 pi over 6, or 30 degrees shy of getting to pi. So my triangle will look something like this, where there's a 30-degree angle in there. And if I have a hypotenuse or a radius of 1, then I absolutely know my other sides. Opposite my 30 degrees is always 1/2, and opposite the 60 degrees is rad 3 over 2. And then depending on what quadrant this point is in, which we are in quadrant 2, I have to go left, which makes my x negative, and up, which makes my y positive. So sine is the y value, or opposite over hypotenuse, but since our hypotenuse is 1, it's just our opposite value of 1/2. And I could do the same thing again and verify that graphically, because both from the left and from the right and the function's value are actually all going to be the same, 1/2. Okay, so let's take a look at number 3 and what this is trying to say. This one we're not going to be able to put in our calculator, so I really want us to focus on what this is telling us. If the limit of the function as x approaches c, if that answer is 4, then let's find these other limits. Well, what I'd like you to notice is that A is asking us for the limit as x approaches the same x value that we talked about above of the function, but now we are cubing it. So the cube of the limit of the function is going to be the same as the function cubed, because again, this limit is an output. So this will be, all of this we said was 4 from above, so this will be 4 cubed. So this is 64. And then the same thing kind of holds true with question B here. I have the limit as x approaches c, so same x value of this function, but you see that square root in there, right? So we're going to square root that limit, which that limit was 4, and so the square root of 4 is 2. Don't mistake that for plus or minus 2, that's just a whole 2. Okay, so let's take a look at number 4 and let's look at some algebra here. My first inclination for this limit would be to substitute 0 in everywhere I see an x, but that gives us something that's undefined rather quickly, 1 over 0. So I cannot do that. So instead what we're going to look at is something we learned in algebra on how to combine these two separate fractions or two terms into one by using a lowest common denominator technique, or really any denominator will work. So if I look at this second fraction's denominator and factor it, maybe you can see that you can factor out an x. So my lowest common denominator of both of these fractions would be the x factor times the quantity x plus 1. So I will rewrite this limit using or trying to get this common denominator. So it'll be limit as x approaches 0. Again, that's the calculus piece. The rest of this is just algebra here. So the first fraction, I'm going to multiply by the quantity x plus 1 over x plus 1. And the second fraction needs nothing. It already has the common denominator. So I will write the limit one more time. I'm still not ready to apply the limit. If you substitute 0 in now, you're still going to get something that we don't know what to do with. So we're still not in any better shape than we were before. Although if I distribute this 1, you're not really going to notice, but my numerator will become x plus 1 minus 1 over this common denominator. So if I write them together as one fraction, I should easily see that that plus 1 minus 1 adds to 0. And then what I can also hopefully see is that x divided by x is 1. So that's going to leave a 1 behind there. And so really what I'm trying to evaluate in the end is the limit as x approaches 0 of 1 over x plus 1. Now I'm not saying for every single x value that these two expressions are equivalent. However, their limits are going to be equivalent. So if I substitute 0 in now, I get 1 over 0 plus 1, which is 1 over 1. So this limit should be a 1. And I could certainly check that graphically. Again, since I'm approaching 0, I would want to check from the left and from the right and make sure that your output is approaching 1. All right, so let's take a look at number 5, which has to do with absolute value. I think a lot of us remember that absolute value is the distance from 0 along a number line, but mathematically speaking, can we define absolute value of x in terms of its piecewise function? So if we think about what does the graph of absolute value of x look like, most of us know that it's supposed to be basically a V is what most students say. Okay, let's think about this as a piecewise. Well, it's one line here on the left, and then it's a positive sloping line here on the right. Both lines are actually y equals x, but here on the left it's got to be the negative x, and here on the right it's the y equals positive x. So it's exactly what we say. For all values less than 0, so when x is less than 0, we are along the line negative x. This should make sense to you because if you put in a number in here like absolute value of negative 3, we know that to be 3. Well, that's the opposite of what you put in. Okay, so that kind of makes sense. Well, now on the right-hand side of this graph, or the green highlighted, when x is greater than or equal to 0, we see the positive sloping line y equals x. So that's the true definition when you are centered at the origin. So since I'm focused in this question around limit as x approaches negative 2, that certainly puts me in the left-hand side or this side right there, x is less than 0. So instead of absolute value of x, because we're only talking about as x is approaching -2, and that is on the left-hand side of 0 or less than 0, I'm going to use this part of the piecewise because when x is -2, I'm probably, let's see, -1, -2, I'm probably up here somewhere, right? So we're going to say limit as x approaches -2 of 2 minus, and instead of absolute value of x, I'm going to say -x. And I hope you can quickly see that this is 2 plus x over 2 plus x. Don't forget your limit as you rewrite, which that does divide to 1. So this limit should be a 1. So let's check this out graphically and see. Okay, now many of us might not know where the absolute value button is, so let me show you on your calculator. So it's 2 minus the absolute value. So it is in math. So if you go math and you go over to this number, it is the ABS, that first choice right there. So math, go over one to the right, and it's right there. You also do have a catalog that is alphabetical, so when you're trying to find absolute value, that's early on in the alphabet. So you could hit second 0, and it's the first one right there, and you would just hit enter. So either way, it'll get you there. Okay, so 2 minus the absolute value, here's another way to find it, of x, and close my parentheses, divided by parentheses 2 plus x. That way all of that stays in the denominator. And if I'm just looking in a standard window, I will see this graph. I'm looking at the limit as x approaches -2. So I'm looking over here. I believe that one probably is correct. Furthermore, what I do also believe is that the limit from the left is equal to the limit on the right, but I can prove that using my table as well. So if I'm in my table and I say something like -2.001 and -1.999, I'm testing from both sides to make sure that that output is approximately the same, and it is. If you try to just substitute in -2 directly, you should get an error, and I hope you saw that immediately, because 2 minus absolute value -2 would be 2, so you'd have 0 in the numerator as well as 0 in the denominator. So I had to do something. Okay, let's take a look at this number 6, which has to do with logarithms. And one thing that you should remember is you cannot take the log of 0 or natural log of 0. The common log would be base 10. So this would be, I'm going to take 10 to some exponent and end up with 0 as an answer, and that's just not possible. So we cannot take the log of 0 or natural log of 0. So if I directly substitute -2 into here, that's exactly what's going to happen, and it's a lot easier to see over here. -2 plus 2, 0. Log of 0 does not exist. So how can I try to evaluate this limit using some algebra that you should have learned, and that I'll remind you of right now, in college algebra? So maybe pause this video. Do you see anything with these logarithms? Do you see a way of combining the logarithms together? Again, pause this video and see if you can do that yourself. All right, hopefully we are all back and we can see that my limit should still be there. So check your work. Do you have limit written down? And then I'm going to put a bracket here just to keep this together. What I hope you remembered is that log of some quantity minus log same base of a different quantity turns into log of that quotient. And that's really because logarithms equal their exponents, so we're really just kind of working with our exponent rules here when we're working with logs. So when we're dividing with the same base, we end up subtracting the exponents, and that's what's happening here. Okay, so I'm going to write one logarithm one time, and then it's going to be that first expression, 2x cubed plus 3x squared minus the 5x minus 6 all over that second quantity, which is x plus 2. I still cannot substitute in, though, that -2, right? Because now I'm dividing by 0. Well, if that's the case, and it's 0 over 0, which it does turn out to be if you substitute in -2, that means that -2 is a factor of each, the numerator and the denominator. So if it's not obvious like it is in the denominator, I can try to factor it out of the numerator. Well, I'm not really sure how to factor that, so I'm going to go to good old-fashioned synthetic division. So I'm going to write the coefficients in perfect descending order: 2, 3, -5, -6, and I show my synthetic division like so, and I'm going to divide it by that -2 because I know that this has a remainder of 0, right? Because I got 0 when I substituted it in, so I know it's a factor. So I'll carry down this first coefficient. This is my multiplier, so 2 times -2 is -4, add down, multiplier, so 2, add down, multiplier, -3 times -2 is +6, add down. You should have gotten 0, right, because that's the remainder, but this is what's going to be left over. So I'm going to rewrite this whole thing here. So I have limit. Again, you don't really have calculus if you don't have the limit. We've technically done the other part, all this blue part, in your algebra course. So I have log of, in my numerator, the first factor will be that x minus -2, or x plus 2. And the second factor is what's left over after my synthetic division. So 2x squared minus 1x minus 3. And now I can definitely divide x plus 2 by x plus 2 to be 1. And so now I just have limit as x approaches -2, log of the 2x squared minus 1x minus 3. You should be able to substitute in a -2, right? Limit as x approaches -2. So this will become plus 2 minus 3. So this will become log of 8 plus 2 is 10 minus 3 is 7. So this is one of those ugly irrational answers, so we're going to see some decimals here in our calculator when we check it. Okay, so what's important to remember here is that I am typing in the very original limit that I want to find. So this log of this whole quantity minus the log of the other one. So I'm looking for this original log of A, basically minus log of B. And I did change my window a little bit. If you want to pause it and take notes, that's fine. I just want to be able to see what I'm looking for. And I'm looking for x approaches -2. Now, one quick thing, when you hit graph, you should never be surprised. Like it's your birthday and you just got this present and you opened it up and you're super surprised, like, oh, we should kind of have an idea of what we're going to see. We might not know the shape, but we should certainly know the domain. So if we look back at this original, we know that x cannot be, for example, -3. Because if I put in -3 just into the second piece, the log of x plus 2, I have log of -1. And we should know that, again, that argument needs to be greater than 0. Okay, that makes sense then that it's not over here to the left. So does it look kind of like a reflective graph? Yes, but it is not going to continue this way. So my limit as x approaches -2 is not necessarily going to come from the right because my function does not exist over here to the right of to the left, excuse me, of -2. So I can't come in from that side. So if I go to my table, I will see exactly that. I'll delete these old ones out. So what I'll see is that if I type in -2, I should get an error, which we kind of knew from the beginning. If I type in something like -2.001, I'm also going to see an error, which is that domain restriction that we just talked about. And if I type in something like -1.999, I should expect log of 7. Well, it's not going to give me the exact answer back. So this 0.84454, I'll go to my home screen and see what is the log of 7 to see if that is close, and yes, it is. Okay, last but certainly not least for this section is something called the greatest integer function. Now this is a function that's going to give us the largest or greatest integer, which is always less than or equal to the x value that we are substituting in. So 0, 0 is going to be a closed point here. I'll do this in a little bit darker of a blue. So 0, 0 is a closed point because if I input 0, I get 0 back out of the function. And if I put in anything along the way, anything up until exactly 1, I'm not quite yet 1. So I can't say that it's of 1's value yet. It's the next least integer. So if I have, for example, greatest integer of 0.9, this is going to be 0. I'm inputting 0.9. It's not quite yet 1, so it still is 0. Okay, so then once I reach 1, this is a whole, because once I reach 1, so if I have, for example, greatest integer of 1, then that is a 1. And there's a couple different ways that you can show the greatest integer function. This is just certainly one of them. So sometimes people also will do it something like that. That's also greatest integer function of x. So you might see it represented in different ways. Okay, so if I give you this graph, and I'm going to continue putting on the points. So once I input a 1, I equal 1. So 1, 1 would be a point on the curve. But once I get to 2, then it equals 2. So this is also called a step function, if you've ever studied that in the past. And this does exist in the negatives, so let me draw at least one over here in the negatives, because this is a step function that will continue that pattern on into quadrant 3. Certainly is not a continuous function, right? They're horizontal lines, so it would be a bunch of piecewise functions put together. So let's see if we can evaluate this limit. So we're looking for the limit as x approaches 3 from the left and then 3 from the right, just looking at this graph. So let me draw the line where x is equal to 3. Makes it a little bit easier to see visually, I think. So as x approaches 3 from the left, you are over here. So you're approaching from the left. So you're along that horizontal line, which would be 2. But as you approach 3 from the right side, you are greater than 3. So you are up here. I don't know if these arrows are helping. So your output is positive 3. So if I asked you, question C, limit as x approaches 3 of this greatest integer function for x, you would say does not exist because, and so hopefully you're familiar with the DNE, does not exist, because the limit as x approaches 3 from the left of your function does not equal the limit as x approaches 3 from the right of your function. I'm not going to just say because 2 doesn't equal 3, because 2 has really never equaled 3. We're talking about the limits. I hope you found this video helpful. Thanks for watching.